Hi everyone. I'm sorry that school got extended to the end of the semester. I'm assuming it's probably not a surprise to majority of you, but I am sorry, especially for those seniors. It's kind of a bummer way to end the year. Anyway, let's talk about activity series today. So we're going to be looking at the factors that affect the potential in a voltaic cell. So I'm going to be going through the POGL that if you are in advanced chemistry will be on page 130 in your lab notebook. If you're in regular chemistry, it's going to be in page 137 of your lab manual. They're also up on the website, and it'll just be on the first page on the website on Schoology. So anyway, let's take a look at a bunch of different metals and see how reactive it is, and then see if we can't rank how reactive it is. These are important things for making things like batteries and other energy producers. It's really important for us to understand the activity series for things. So we're going to investigate that using this lovely simulation designed and created by Dr. Tom Greenbaugh. So thank you to him for doing this for us. All right. Okay, let's go. So let's go to activity 1. All right, so in activity 1, we're going to take a bunch of magnesium strips. You can see these magnesium strips. We're going to dip them in a bunch of different solutions. All right, so let's dip them in. We're going to wait, see what happens. Now we're going to pull them out. Now I want you to write, I would write a table up for all these observations. Here I don't see any changes. You can see things got plated on each of these things on our magnesium. So we have zinc plated on our magnesium here. We've got copper plated on our magnesium strip here. And then we have silver that plated on our magnesium strip here. All right, let's take a look at copper. Let's dip it in. And now we can remove it. Okay, write down your observations here. So I don't see any coating that happened, no reaction happened in these first 3, but something did happen between the silver and the copper. All right, so this is all just writing down your observation for activity 1. This is number 1 in your activity series POGL. All right. Let's look at zinc. We're going to dip it in. Wait a second for it to react. Oh look, it's done reacting. Move it out. All right, nothing happened with these two. Definitely got some reaction happening here. Let's do our last one with silver. See if we get any reactions and then pull it out. Oh my goodness, nothing happened with silver. How bland. Okay. So, now based on what you observed here, go on to, so write down all of your observations. Like I said, I'd recommend a table saying, magnesium dipped in magnesium, copper dipped in magnesium, zinc dipped in magnesium, etc. I'd recommend writing, what I did is I did the metals up top, so I did magnesium, copper, zinc, and silver, and then going down, I did my solutions. I did the magnesium nitrate, the zinc nitrate, copper nitrate, and silver nitrate. Anyway, hopefully you set up a table that's logical to you and just wrote whether or not there was a reaction or coating that happened. Now, number 2, a metal that loses electrons more easily than another metal is said to be more reactive. All right, so less reactive metals will play on to more reactive metals, considering magnesium, zinc, copper, and silver. Which of the 4 metals you tested is the most reactive? So based on what we were looking at, which metal was the most reactive? Which one of those metals that we dipped into a solution had the most reactions across the board? All right, and then which is the least? Then go ahead and arrange the metals in order of increasing reactivity, starting with the least reactive metal up to the most reactive metal. Okay, so now let's look at activity 2. We're going to do the same thing again. I want you to write up a table for yourself We're going to dip some iron into each of these solutions. We're going to let it react. Pull them out. Okay, record your observations here. I'm just going to crank through these so you can pause and such as needed. Okay. Woo, nothing happened with lead. How boring. It was like the silver before. Okay, keep on moving. Oh, I was a little too excited to try to move it out. Okay, here we go. There's nickel. And now let's take a look at tin. All right. I'm going to move on to activity 3. It's the same thing with just different reactions happening here. We're going to dip iron into each of these solutions. And remove it. Write down your observations. We're going to dip copper down into each of these. Give it some time to react. Now we can remove it. And then we're going to put some zinc in. And now it's done reacting. We can remove it, write down those observations, and this is plated here. It's just the same color. Okay, and last but not least, now we can remove it. Okay, so write down all those observations, so that gets us through number 4. Okay, so now we're going to locate the 8 different metals in a standard reduction potential table. So this will be at the end of your POGL. It should look like this. So if you flip to the end, either in your lab notebook or online, it'll be the last page of the POGL. This is what we call a standard reduction potential table. Okay, so it's got a bunch of half reactions, right? Our half reactions is where we have the electrons and what's going on with the electrons in each of these. Okay, so let's take a look at this. If I were to find, let's just look at the first 4 that we did in activity 1, just so we're not finding them all together. I think you can find them on your own too. But let's just find a couple. Okay, let's see, we did magnesium, which I have here is negative 2.39. Okay, going on up, I can next find zinc as negative 0.76. Continuing up, we worked with copper, which is 0.16. So keep in mind that's now positive. Actually, I'm sorry, let's do this copper. 0.34. Since we weren't working with an ion, we were working with the metal as a solid. Anyway, 0.34. These are all in volts. If you recall from day-to-day life, you measure things like batteries, etc. in voltage. So this is in voltage, or the volts. And then the last one that we did in that first was silver, which is right here, 0.8. So take a look and see if you can see a theme between where things are located in the standard reduction potential and how that compares to, if you look back at 2C, how you arranged in order of increasing reactivity. How does that then compare to the number, the voltage, the reduction potential given on this table? Alrighty, so I want you to write that observation down. That's going to be number 5. All right, let's go back to our activity here. We're going to do the last one. We're going to look at number 4. And 6, I want you to write down those oxidation reduction half reactions. Let's move on to 7. So we're going to do activity 4, the rate at which bubbles are produced. Okay, so we stick silver in. All right, I'm not seeing anything happening. Oh, I'm apparently too excited. All right, and on the molecular scale, things are bouncing around, but nothing's really happening. All right, let's remove it, and let's do a new metal. We're sticking it into HCl. All right, so copper when stuck in. Well, I'm not seeing anything happening here either. All right. So again, on the molecular scale, no, I'm not seeing anything. Nothing's happening with the copper. It's not reacting with the H plus ions in HCl at all. All right, let's take a look at nickel. Woo! Bubbles! Look at that! So I would say there's a bit of a reaction. Let's see what's happening on the molecular level. Ooh, those H plus ions are coming and reacting with the nickel, making it dissolve into the solution and pulling it off of the metal there. Okay, let's remove that. Oh, look, you can see it got smaller, which makes sense because it was reacting and those ions were leaving. Let's do lead next. Woohoo, more bubbles. Again, molecular scale here. You can see that lead is a much bigger element. Here again, it's going to create all these ions when it interacts and creates H2 gas. That's H2 gas are the bubbles that we're seeing. Okay, and when it's removed, you can also see that there's a decrease in size. Last but not least, and then again we see bubbles with tin on the molecular scale. It's coming in, it's reacting with the tin, creating H2 gas and tin ions. And when we remove it again, we see that that's decreased in size due to that. All right, so write down all your observations and your POGL, and then go through and answer the questions in the activity on Schoology. This is all very important because it applies to batteries, which is and other things that function similar to batteries, which I will talk about in more depth for the next day. All right, hope you're all hanging in there.